Good afternoon, ladies and gentlemen. I have the pleasure today that introduce Mr. Filipov, who is a professor of engineering school of Nancy in France. Professor Filipov is doctor from Moscow Institute of Steel and Alloy. Also is doctor in geoscience and is the main research director of the main research area, Fundamentals of Flotation Process. Today the presentation is quite different than the previous one, because Professor Filipov is a person recognized at the international level how a professor in flotation. Flotation is a concentrate system that is necessary to make from the minerals when coming of mine for increase the load of metals. The system is into the gravity system and is used in the copper industry, in the zinc industry, and in the lead industry. So it's a very important technology for increase the load of the mineral that coming from the mine before introducing the metallurgical plant. Today, the explanation is more theoretical than the previous one, but if you have some question, please ask him, because it's necessary that you understand the technology and the system for do that. So, Mr. Filipov.
Okay, thank you. Thank you very much. Good afternoon or good evening. Yes, I will try to explain what is a flotation in 2 hours, maybe slightly more, yeah, less. And these topics I teach for my student geologists in Nancy during 1 week. Okay, I will try to resume the main step of flotation process in 50 slides. This is a difficult task for me this evening, but we will try together to arrive at the end of this presentation. Okay, flotation is a process which is used to process mainly ore for non-ferrous metallurgy, and to understand the volume of ore processed by flotation. This volume may be compared to the volume of erosion process at the geological level of Bay. Yeah. This means that flotation process is 2,300,000 ore per year. This very big volume. Principle for, we will try to explain the, there is a pointer here, yes. Yeah, we will start by flotation principle, some very the basic principle, physical chemistry principle of flotation. I will explain what means a collector, what means a depressant, and how we keep a small bubble in a flotation cell using Frother. I will focus on sulfide mineral flotation and give some case study. The flotation is a selective separation of hydrophobic mineral particles from hydrophilic particles with the aid of chemicals and gas bubble. This means that we use chemicals to change the hydrophobicity of mineral particles, and we use gas bubble to separate hydrophobic particles from hydrophilic particles. The area of flotation is between 10 and 500 microns. Usually for sulfide ore, we can decrease the particle size up to 5 microns, and below 5 microns particles are too fine, and the reagents and chemical consumption increase significantly, and the economy of process is not acceptable for some ores in this case. And for coarse particle, between 150 and 500 microns, the particle are, depending on the density, are too coarse and impossible to recover this particle by flotation. And for coarse particle, you know that this is gravity processing, which is more useful to use. Before starting explain the flotation fundamentals, I would like to show where is the processing. You start by the run of mines. Ore is processed and generate concentrate and waste. Concentrate is used by the metallurgy to produce some useful object for our consumption, manufacturing object, and after the manufactured object is used and becomes as a waste. And ore dressing objective is to transform raw ores to a concentrate, which is a product used by the metallurgy. Because the cost of metallurgy process costs money and energy reported to 1 ton of raw ores is higher for metallurgy process compared to physical processing. Due to the mineral processing is situated between mine and metallurgy, and the mineral processing is depending on the ore property, mainly on the mineral composition, textural property, and a size of mineral particle. Okay, and the other concentrate grade is depending on the metallurgy process to be used to process this concentrate. For example, if we focus on copper ore, if you process ore which contains mainly chalcopyrite, you can go up to 28% of copper in concentrate, because in the chalcopyrite we have only 34% of copper. You cannot go to 50%. This means the process concentrate is limited by the mineral which is contained in the ore. And after, you need to ask your colleague from metallurgy if 28% of copper in concentrate is acceptable for metallurgy process. We have two limitations. The ore grade and concentrate grade. Okay, then main goal of flotation is to starting from raw ores with low grade, increase the grade and allow the metallurgy to extract the metals from this ore. For this, we use several separation process, but you know that ore is presented, run of mines is presented by the block, mineral block. Rock is not the separate particle. To apply the processing, you need some crushing and grinding step to liberate useful or target minerals from gunk particles. This step allows to go from 1,000 millimeters to several microns or several hundred microns. This means the reduction rate is very, very high. Okay, and objective of crushing and grinding is obtain the mineral liberation. Because we apply, after this liberation, the separation of different minerals using some physical difference in physical properties, such as, for example, density, magnetic property. For example, if you work with the iron ores, you have quartz particle, you have also magnetite. This is a mineral, iron oxide minerals, which has a magnetic property. Using the magnetic separation, you can recover the magnetite and direct the quartz particle to tailings. Okay, after processing, you have two products: concentrate and tailings. But for example, for this flow sheet of processing of copper ore in from Aitik deposit in Sweden. This is the north of Sweden. This is porphyry copper deposit with very low content in copper. After drilling, blasting, you obtain the ore, which is directed to the crushing plant, where you reduce the block size from 1 meter to several millimeters. After this millimeter-sized particle feed the autogenous grinder here, it's 30 meters of diameter, and with 2 steps of grinding, you liberate the copper particle, mainly this chalcopyrite particle, from gangue minerals and from pyrite. And after you perform the flotation process, you obtain the flotation concentrate after the solid-liquid separation. The name of this process is thickening. You perform the filtration and you send your concentrate to metallurgy plant. This is monometallic ore. We have only copper. It is easy to process this ore, but this picture presents the plant, but it's not very good color here. This is a grinder, primary grinder, secondary grinder. Yeah. When you have for more complex ore, and you can concentrate flow sheet, you use it more complex. Why? Because in these polymetallic ores, you have copper, lead, and zinc minerals. But all these minerals are sulfide minerals. And this means that if you have the sulfide, the property are the same. In this case, you need to combine several flotation steps to separate copper, chalcopyrite, galena, and sphalerite to have 3 concentrates. Because the requirement for the is that you need obtain to be economic. You need obtain 3 separate concentrate. Okay, and how perform this separation? This is challenge. Okay, and my task today is to explain how from a complex polymetallic ore, combining some the flotation step, combining the collector, depressant, and the activator, you will obtain design this kind of flotation plant and obtain the 3 concentrate. This means we need to understand what means hydrophobicity and hydrophilicity. This is some fundamental or basic property of the mineral water interface. This means the surface of minerals which is in contact with water. And when water is on the mineral surfaces, water attached to the mineral surface, we have so-called hydration process. And in the nature, the most of mineral particles are hydrated and are hydrophilic. What means hydration or hydrophilicity? Hydrophilicity means that water wet the mineral surfaces. Water wets the mineral surfaces. And to attach this particle to the gas bubble, we need to change the surface property. For this, we can use some flotation chemicals, which change the surface property of target minerals to hydrophobic, and therefore the particle can attach to air bubble. But surface property of minerals is defined by the fragmentation. It means that before, as I mentioned it, before start the separation process, you need to liberate target mineral. For this, you use grinding process. Grinding is divide the materials and generate some broken bonds. The generated generated surfaces, you have the surface charge variation or modification. You have some the side charged negatively, some other charge sides positively. And if you perform the grinding in the dry or wet atmosphere, you can you minimize the thermodynamically the energy by the gas adsorption or by the adsorption of water molecule. And the adsorption of water molecule is controlled by the water dissociation and interaction with the mineral surfaces. If we try to analyze what happens on the quartz surface, we will observe, we will obtain very strange or surprising result. Quartz is known as a inert mineral, is not reactive minerals. But when you use the fragmentation, you apply fragmentation to quartz, you generate the site which is negatively charged, and this negatively charged react with a proton produced by the water dissociation, and the surface of quartz becomes hydrated. And the surface is presented by hydroxyl groups. And if you have a positive charge, the hydroxide generated as by the water dissociation react with the positive charge and create other hydrated surface. And because this is weak acid, the surface charge of quartz is negative in the pH range from 2 to 10. It's negatively charged. This means that quartz, which is inert minerals, have negative charge on surface. By accepting this, we can act now to, for example, change the surface property of quartz by using some chemical which are charged positively. And by electrostatic the mechanism, we can adsorb some molecule on the quartz surface. This approach is used in the flotation. But what happens when we use the chemical to change the surface property? First step in the mineral water interface is the interaction of the mineral surfaces with water. And we have the two main phenomena which occur simultaneously. This is first one is the destruction of when we add the chemical, we have two phenomena. First one is that we start to change the structure of water in the interface, and second step is the adsorption of the chemical on the mineral surfaces. And this interaction, these two steps, results in the changes of surface free energy. And surface free energy reported to the 1 square centimeter of the surface is called surface energy. And if you measure this energy at the gas liquid interface, in this case, you call this energy as surface tension. This this is not a parameter which is disconnected from minerals. This parameter characterizes very well the surface property, and you can understand this if we analyze what happens with the water drop when we put this drop on the mineral surfaces. This is polished section, for example, and according to the wettability of mineral surfaces, you can have this kind of profile of the water drop, or you can have the very good spherical form of this drop. The form of water drop on the surface depends on the hydrophobicity of mineral surfaces. Yeah. At the equilibrium state, we can measure the contact angle value, and this contact angle translates very well the hydrophobicity of mineral surfaces. If contact angle value is higher, surface is more hydrophobic. If contact angle is low, in this case, if the value of contact angle is low, surface is more hydrophilic. And using the surface energy at 3 interface, the surface energy at the interface solid gas, interface liquid solid, and liquid gas, you can calculate the contact angle value and define the hydrophobicity of mineral surfaces. This means that you no need to change the hydrophobicity of all minerals. You try to change the hydrophobicity only of target minerals. For example, in your ore, chalcopyrite is target minerals. You will try to absorb the chemical to change the hydrophobicity, to increase the contact angle only on the chalcopyrite particles, and not on the quartz. Okay. And when you change the surface property of minerals, mineral particles, you put this particle in a flotation cell. This is a reactor with a rotor system which allows to put in suspension of mineral particles, and small particles are distributed inside of flotation cell, and after you introduce the bubble in this reactor. And the size of bubble is fixed, for example, between 1 or 2 millimeters, and the bubble floats to the surface of the mineral, of the pulp, of the water. And when floating, the bubble enter in the contact with the particle, and this phenomena, collision between bubble and particle, is mainly depending on the particle size and on the bubble size. According to the surface property, some particle attach to the bubble, and these particles are transported with the bubble, with the floating bubble, to the liquid surface, and where they form frost phases. And by using some mechanical ways or auto evacuation, we can evacuate and separate the hydrophobic particle which attached to the bubble from a hydrophilic which still in the reactor. This means that we have at least 3 main flotation sub-processes. First one is a contact between particle and bubble. This processes, sub-process is called collision. Second phenomena is the attachment. Attachment depends mainly on the hydrophobicity of mineral. Only hydrophobic particles attach to bubble and are transported to the frost phases. This is a second step. And third phenomena which can occur in flotation cell, some particles which arrive to frost because of the coalescence in the frost phases can return to the pulp. This means that we performed some work to attach the mineral particle to the bubble after we lose this particle, because the particle which is controlled by the drop pack phenomena are lost for concentrate. Those flotation process operate in a three-phase system with a solid mineral particle, liquid phases which constitute the pulp, and with a gas bubble. Main phenomena which controls the flotation efficiency is a phenomena as an interface, and we also have three interfaces: solid-liquid interface. This is interface of the mineral particle with water; liquid gas, which controls the bubble size and bubble stability; and solid gas. What means this interface? This interface is an interface when particle attached to bubble. Here we have so-called the contact perimeter, which controls the force of attachment, the attachment forces of particle to bubble. Because your bubbles are floating in the hydrodynamic environment. This means that your rotor creates some turbulences which can impact the stability of bubble particle. Those flotation process is controlled by attachment as a detachment processes. Attachment is controlled by the hydrophobicity, and detachment is controlled by hydrophobicity and also by turbulences created in the reactor. Those we need to control not only chemistry of flotation process, but we need control of the hydrodynamic of the flotation reactor, flotation cell. And because the flotation is composed from several macro processes, so sub-processes, in this case, to develop the flotation model, we need model separately each sub-processes. Okay, we did understand what happens, what is the controlling parameter of each sub-processes. This is some very quick presentation of collision phenomena. This collision starts by the approaching of particle to bubble, but main physical chemistry phenomena is the film thinning, and after the rupture of this thin film. When you approach a particle to bubble surface, you create so-called thin film of water, and if particles are hydrophobic, you obtain rupture of this thin film. If particles are hydrophilic, there is no rupture of this thin film. And attachment produces only if you have rupture of thin film between bubble and particle. Okay. If you know the particle size, this is very easy to obtain this result, because in the plant you perform periodic sampling of grinder. You know exactly what is the particle size obtained after grinding. This is usually less than 100 microns. Okay. 60 microns, 70 microns, etc. If you know the bubble size, this other parameter which you control in your flotation cell. You can, using this simple formula, calculate what is the collision probability between particle and bubble. And this means the collision probability depends, I repeat that, on the particle size, bubble size, also on the hydrodynamic of the flotation process, which is defined by the Reynolds number. You know what is Reynolds. And if you have in your flotation cell the Reynolds number between 1 and 100, this means you can apply this model to control the collision probability between one bubble and one particle. But the real situation is more complex, because you operate with several bubbles. Million bubble in our industrial flotation cell and million particle. In this case, you use another formula which has the same significance. Intensity of collision depends on particle size, of bubble size, also on the energy dissipation in the system. Energy dissipation in the system is related with the turbulence in your flotation cell, and also depends on the viscosity, which translate the solid percentage in your pulp, and also, of course, of the solid density of minerals and density of water when you use. This means that for modeling purpose, you can use the previous formula here, but only for one bubble and one particle. When you operate in a flotation cell, you need to use this formula. Flotation and the final efficiency of flotation, so call it collection efficiency, is the product of collision probability, attachment probability, and stability of bubble particle created. We have three main factors which influence the collection efficiency in a flotation processes. This is collision probability, which depends on particle size and bubble size, and also on the intensity of turbulences. Attachment probability, which depends on the hydrophobicity of particle, and also on the hydrodynamic and stability of the system. Here you have the experimental data which show that increasing the bubble diameter, you decrease the collection efficiency. You float better with a small bubble. But what is a problem with a small bubble? Of course, this increases the collection efficiency, but this decreases the residence time in a flotation cell, because small bubble velocity is low compared to big bubble. Okay, this needs in a flotation cell. You need try to find a compromise between efficiency and the capacity of reactor you use. Okay, for this, the producer of flotation cell try to optimize the all processes. For this means the flotation industrial flotation cell need generate the small bubble to have the high efficiency of the flotation, but other modern flotation cell controls the mixing inside of flotation cell, because mixing create high turbulency. High mixing is high turbulency. If you have high turbulency, you will decrease the stability of bubble particle. This means you will favor the detachment processes. And for this, in a modern flotation cell, you have some kind of disposal of the rotor system, as here, to create several contours of circulation inside of flotation cell. And in each area, you favor one of three parameters I showed before. This means that you favor the collision, you favor the stability in the still zone, and you obtain good result in overall flotation efficiency. For example, this is the smart cell of WEMCO. This design is for 350 cubic meters of volume. This is bigger than this our room here. Okay, Dole Oliver system, several. You can see that we have not only three circulation contours, but also we have some sub-contour of circulation inside of a flotation cell. This means here you favor not only fine particle flotation, but also coarse particle flotation. And this is modern trend in design of flotation cell to create big volume cell, and not only for FL Smith as previous cell, but also for Orthotech, for example, company main trend is the increase the cell volume. This is 300 cubic meters, but in Kevitsa mine in Finland, they already 500 cubic meters is used in main operation. Only one cell is installed. Compared, for example, here you have the several big sized this was yes, the 160 cubic meter of smart cell in Escondida mine in Chile, but in the Kevitsa they use only one big cell. Okay. Another cell which is used in the industry is column flotation. Column flotation, compared to mechanical flotation cell, because previous cell I explained to you the mechanical flotation cell because of rotor which try to mix the pulp, mix the pulp in the cell. In the column flotation we have any moving part. The pulp is introduced at the top part of the column. This is column height is between 10 and 15 meters. 10 and 15 meters, and particle settle inside of column, and at the bottom part of the column we generate a small bubble, 1 and 2 millimeters, and the floating bubble, the rising bubble, made the particle, and if particle are hydrophobic, they attach to the bubble, and particle are removed with the frost phase in the concentrate. Okay, there is several phenomena which we need to control inside of other column flotation, such as the superficial feed velocity, superficial gas velocity, and in a flotation column ratio between these parameters, this means the feed volume and the gas volume, this main parameter which controls the efficiency of flotation. And last trend in the design of flotation cell is the introduction so-called the reactor separator system, in which we have no classical flotation cell. We introduce the pulp and gas inside of a bubble generator, and flotation occurs in a column, small diameter column, which is called downcomer, and the diameter of this comer is between 80 and 200 millimeters. This is a small column, and in this column you perform the flotation in 10 seconds only. While in the conventional flotation cell, residence time is between 15 and 20 minutes in average. This means we reduce significantly the residence time. And all processes, attachment and collision, occur inside of downstream. And separation is performed in the separate part, in the separator part of the flotation cell in very still conditions. There is no turbulences. This means we optimize the collision and the collection in the downcomer, and we optimize the bubble particle transport by the bubble in the still separator part. And this change concept of flotation. Unlike the conventional flotation machine, reactor separator operation depends on the time of contact, while in the classical conventional flotation cell, the efficiency of flotation depends on the residence time. Okay, this is some, okay. If you have question to ask before here, okay. This the design of Jameson cell. You can see that the bubble generator is have bubble generation system have very simple design. We generate a turbulent jet, and the shock impact between this jet and the pulp surface creates a small bubble, and instantaneously this bubble are in contact with the mineral particle, and you create bubble particle aggregate in this part, as here. So, okay, and after the bubble with the particle directed to the separator, and you use, I mentioned that the diameter of downcomer is small, okay? But for high capacity cell, you use several downcomer, place it as hydrocyclone, for example, in the battery of hydrocyclone, okay? Jameson cell now is used, this becomes as a conventional flotation cell. There are several other modifications of this kind of flotation cell, okay? If you have good flotation cell, you have good ore, you need now think about the chemicals you will use to perform the separation, okay? In the flotation process, we use several chemicals, and there are three main family of flotation reagents. First family is a collector. Collector change the surface hydrophobicity of minerals, and these are surfactants, and which acts with the mineral surfaces and destabilize the water structure on the mineral surfaces. This main collector you need to select before starting the feasibility study, for example, on your ores. If you have several sulfide in your ores or several minerals which have the same property, surface property, you need use also some regulator. And we have two family of regulator. First one is a depressant, and second one is the activator. And the depressant or activator help or prevent the absorption of collector on mineral surfaces. For example, if you use one chemical which may absorb on two minerals, but you need absorb this chemical only on one mineral surfaces, you need to use some regulator to block the surface of second minerals. You absorb only one surface. Okay, the reagent family is the organic or inorganic salt and polymers. These two families of chemicals act on the solid-liquid interface. This means that this collector, these chemicals, change the properties of mineral surfaces. To regulate the gas-liquid interface, this means that to regulate the bubble size and bubble stability, you need to use Frother. This is the third family of flotation chemical used in the industry. Now, what is the role of collector? More precisely, Taggart in the 19th century already pointed the essential prerequisite to separation by flotation is selective collector coating. This means that to separate two mineral particles, you need found the selective collector, which will selectively absorb on the minerals, target mineral surfaces. And this is a main step of flotation when you change the surface hydrophobicity to create stable bubble particle aggregates. If you in the sulfate minerals, mineral flotation, some minerals exhibit the natural hydrophobicity. For example, due to some oxidation phenomena in ore, you can have chalcopyrite which floats with no collector. But this phenomena is very limited. Usually, you have hydrophilic minerals. You have no hydrophobics, except some naturally hydrophobic minerals such as molybdenite, some minerals of some sulfur of arsenide and other minerals, or for oxide or talc minerals. We can use even when you float the talc, for example, you need add small amount of collector because hydrophobicity of these minerals depends on the textural property. For example, for talc, you have layered structure. On the lateral surfaces, you can have some other hydration, and this means that even totally is hydrophobized by some area on the talc surfaces is hydrophilic. And for this, you need to use the small amount of collector. But I repeat that for major part of minerals, you need to use a collector. And choice of collector is not easy task because the collector are rarely specific or selective. Collector you use adsorb on the several minerals surfaces, on the surface of several minerals. But this means the adsorb on the target minerals, valuable mineral surface, and other on the gangue mineral surface. The mineral surfaces are not the same in the ore. You have some variability of mineral surfaces. Even in the one deposit, depending on the zone, exploitation zone, you can have different surface property of the same minerals. For example, galena or chalcopyrite may be more oxidized at the surface zone and less oxidized or not completely oxidized in the depth zone of deposit. Same mineral with different crystal structure and chemical composition also have a different surface property. Okay, you need to take into account also this phenomena. And main difficulties related with the substitution on crystal lattice. In some deposit you have substitution, and in other deposit you have any substitution. Indeed, you need to understand what happens when you have additional metal cations, for example, in some mineral. After you have that, some mineral is locked or interlocked is an ore, and you need to take into account the composite particle also in your ore. Nevertheless, we can cite the collector for flotation. For example, if you float the sulfide ores, you will focus on following collector, on following family of collector. Widely used family of collector is xanthate. Xanthate, this is the salt of xanthic acid, which is composed from functional group. As here, this is the sulfidyl functional group and the hydrocarbon chain. All collector are composed from two parts. This is hydrocarbon chain and functional group. The length of hydrocarbon chain may be different. For example, for xanthate family, you can use ethyl xanthate, but we can use other isopropyl xanthate, butyl xanthate, or amyl xanthate. The length of hydrocarbon chain influences the hydrophobic property of collector. With short hydrocarbon chain, you have very strong collector, but hydrophobicity is low. By increasing the length of hydrophobic chain, you increase the hydrophobic property of collector. If you would like float all sulfide, and if you have high hydrophobicity of collector, you will use amyl xanthate. If you would like to use a very selective collector, in this case you use ethyl xanthide. Selectivity and collector strength is inversely related. For selective collector, you need to decrease the hydrocarbon chain, and for more hydrophobic, you increase the hydrocarbon chain. And it's not your task to change this is task of collector producer, the chemical company, but engineer ask chemical company to provide, for example, ethyl xanthide for selective separation and amyl xanthide for bulk sulfate flotation. Second family of collector used in sulfate flotation is the dithiophosphate. You can see that in the sulfhydryl functional group, we change its carbon atom to phosphorus. And this change significantly the electron distribution in the functional group by decreasing the collector forces, but increasing the selectivity. Dithiophosphate are more selective than xanthate. So xanthate is more strong, but less selective. And but how choose between two collectors? And in the industry, task was solved very easily by using the blend of two collectors. Main sulfate mineral flotation plant, the company used a blend between xanthate and dithiophosphate. Okay, this allows the easily regulate the selective separation of sulfide. Some other collector here as also as mercaptan, but it is very strong collector, but very also expensive. Using mercaptan, you increase the cost of chemicals by four times. This is an economic parameter. Another thing is it not very good collector for environment, okay, environmental aspect. Very interesting collector is dithocarbamate. If somebody works on the hydrometallurgy, this is known also as a solvent in hydrometallurgy, but the cost also is higher. For copper nickel sulfate ores, you use the blend between xanthate and dithocarbamate to separate pentlandite from chalcopyrite. And for base metal flotation, copper, lead, zinc, you use blend between xanthate and dithiophosphate. This is the main approach on the approaches used in the practice of sulfate ore flotation. After I would like to present what are the collector used for oxide minerals. This is mainly fatty acid. This is French. Sorry, I put in French. Yes, yeah. This is fatty acid collectors. Fatty acid collector, and main part of fatty acid. This is the oleic acid. You can see that the length of hydrocarbon chain for oxysalts, the oxysalt is higher compared to sulfate mineral flotation. Because for sulfate, we need more selectivity, and for oxide, we need collector strength. Okay. The fatty acid, alkyl sulfate, alkyl sulfonate, also hydroxamic acid. Okay, this is a four main family widely used in the oxide mineral flotation. Oxide mineral flotation, but as for sulfide mineral, xanthate is more widely used. For oxide minerals, this is fatty acid, which dominate the market of the chemicals in flotation as chemical flotation collector. Also, there is another family of collector, these cationic collectors. These cationic collectors is used mainly to flow the silicate minerals, such as quartz. I show it because of the charge, positive charge of the molecule. By electrostatic mechanism, you can adsorb on the mineral surface and float the silicate minerals. You can use the primary amines, quaternary ammonium salts, but for iron ore flotation, for reverse cationic flotation of iron ores, more precisely. Now the alkyl ether amine, alkyl ether diamine is used as main collector. Reverse cationic flotation started with the primary amines, but now ether amines dominate the reverse cationic flotation of iron ores. In Brazil, in Australia, Ukraine, this chemical is used as collector for reverse cationic flotation. Structures collector, you have two parts, as I mentioned, functional group and hydrocarbon chain. Hydrocarbon chain, this is aliphatic chain as here, composed from the methyl and methylene groups, by changing the length of hydrocarbon chain, you change the hydrophobicity of collector. The design of hydrocarbon chain also is interesting way to change the collector property of molecule. For example, introducing the some aliphatic chain and create or branching the of hydrocarbon chain, you can increase the selectivity of collector. Several years ago, the people used the aromatic group to increase the hydrophobicity, but since 15 years in Europe we cannot use this way. But in China, for example, some collector as styrene phosphonic acid is widely used to float because this increased significantly the selectivity of collector and collector stage. Now I will switch to the sulfide ore flotation. And we will try to understand what happens with sulfide ore, for example, with copper sulfide, when we perform the grinding, and which is a phenomena which control the separation process. For this, we will analyze the reactivity of the sulfide ores. We have sulfide minerals. This is composed from metal ions and sulfurs. And when we decrease the particle size, we increase the reactivity of mineral particles, and two kinds of reaction happen on the mineral surfaces. First, the kind of reaction which occurs is related with the oxidation of the sulfur, which is in the state -2 in the minerals. And in the contact with the water and the air, we change the oxidation state of sulfide from -2 to +6, and by creating sulfate groups or thiosulfate groups. And the domination of sulfate or thiosulfate depends on the pH and also on the redox potential in the system. These are two parameters which control sulfate state due to the sulfur oxidation. This is pH and redox potential. Okay, and to optimize the collector adsorption, we will see later, you need to keep constant the pH and redox potential. After the second family of reaction which occurs in the contact with the mineral with the water, it is a reaction related with the transition metals. This means if you have hydroxyl in your system or sulfate or thiosulfate, you can create the hydroxide of metals. You can create thiosulfide and sulfate of metals. And all these reactions occur on the mineral surfaces. Minerals still unchanged. Only a molecular layer of the surface changes by this reaction. This is not oxidation of all particles. Only, I repeat, the surface, mineral surface change. When you use xanthate, I remember the xanthate is this one here. You have the the functional group, this sulfhydryl group, and this group is composed also from sulfur. And xanthate change also in the system because the xanthate can, in the contact with the oxygen of air, can oxidize and form, say, call it dixanthogen. This oxidation reaction change the state of molecule. If you have xanthate in water, is presented mainly by the anion. And, if you have oxygen in your system, you have this oxygen in the system, you can oxidize and decrease the anionic state of xanthate and increase the non-polar state of dixanthogen. But the adsorption is controlled by ionic state of the molecule, not by non-polar state. This means if you totally oxidize your xanthate, you have no more collector in your system. Phenomena is more complex because oxidized state, this dixanthogen, is hydrophobic. This means that you can have mixed collector, a mixed adsorption layer, which composed by the chemically adsorbed xanthate and physically adsorbed micro drops of dixanthogen. In this case, the oxidation state of minerals increased significantly. This means that you need control also by changing the pH and redox potential, you need control of the state of collector. First one, you need control the surface of minerals. Okay? If you totally oxidize the surface, you will have no more possibility to adsorb the collector. If you oxidize totally the collector, you have no more collector available for adsorption. And the stability of xanthate and the control of surface state is the two key factors controlling the sulfide mineral flotation. Not only chalcopyrite, but all sulfide mineral flotation. Task is not easy, but in the literature you have a lot of information available for different minerals. You can use as first step in your feasibility study this information to start your investigation. I precise that the efficiency of flotation is controlled by the collector adsorption, and the collector adsorption depends on the solubility product on new formed phase on the mineral surfaces. If you have the sulfide minerals such as sphalerite, galena, chalcopyrite, or pyrite, if you use the ethyl xanthate, X means this is ethyl xanthate. You need to compare what is the solubility product of the xanthate with the metal cations on the mineral surfaces. And after, you need to compare the solubility product with the sulfate. If you want to float the sphalerite, you use the ethyl xanthate. This means that you will form ethyl xanthate of zinc on the sphalerite surfaces. Okay, but sphalerite is presented by the sulfur of zinc, which solubility product is very low, 10-23, and compared to ethyl xanthate solubility product, you see that the ethyl xanthate is more soluble. This means that thermodynamically, you cannot form ethyl xanthate on the sphalerite surfaces. This means the sphalerite cannot be flowed with the ethyl xanthate. If we would like, for example, to compare with the galena also. Galena, you adsorb the ethyl xanthate on the galena surface, you form the ethyl xanthate of lead. But sulfide state is also more stable because the solubility product is significantly low compared to ethyl xanthate. This means the galena does not float with xanthate also. And the same situation is with the sulfide of copper. But people use xanthate in the plant to float the sulfate. Why? Thermodynamics is not in, doesn't corroborate with the real practice. Because the problem is not with the thermodynamics, problem is the consideration you make on the mineral surfaces. Because in your system, the surface of this mineral is not presented by sulfate, but sulfate changed. The pH 6 is optimal for flotation. For arsenal pyrite, you have 8, and etc. This means using this table, you can use the optimal pH for flotation of different sulfate minerals. For some minerals, such as sphalerite, you need to activate surface, because we already mentioned that the sphalerite doesn't float with the xanthate. This is experimental data obtained which shows that there is no flotation, or recovery is very low for sphalerite. And when you use the copper sulfate, which adsorbs selectively on the sphalerite surface, in this case, you increase significantly the flotation recovery of sphalerite. Okay, after this, you can decrease the floatability. Activator increase the floatability of minerals, but depressor decrease. You can use some organic depressor, such as carboxymethyl cellulose, starch, quebracho, etc. Using the different molecule, you can control the interaction mechanism and choose your depressor for target minerals. And adsorption of depressor will change the hydrophilicity of surface by rendering the surface hydrophilic and avoiding the interaction with the gas bubble, which the surface is hydrophobic, but adsorbing of the hydrophilic group of molecule of depressor, you increase the hydration rate of mineral surface and avoid interaction with the hydrophobic gas bubble. From inorganic depressant, I will mention cyanide, because cyanide is a most popular depressor, a most efficient popular depressor used for sulfate mineral separation, for example, for chalcopyrite separation. Okay, here there is several mechanisms which occurs on the mineral surfaces, but I will focus on two factors which limit the use of cyanide in the sulfide mineral flotation. First one is the environmental problem. Okay, you cannot use with no control cyanide as a chemical in your flotation. You need control the environmental impact of cyanide. Okay, you need avoid any contact with underground water. This is first parameter. For this, people use biodegradation or the mean to destabilize the cyanide group in the tailings. Okay. But if you control this parameter, you need to take into account a second factor, the presence of secondary sulfide mineral of copper. Chalcozite and covellite are soluble minerals of copper, and using cyanide you will promote the transfer of copper from solid to liquid phase. And when you transfer it, this goes with the tailings. You lose copper. And in some plant, the losses, the level observed in practice were up to 20% of copper lost with the tailings. And another thing, if the content in precious metal, on gold and silver is higher, you cannot use cyanide because this solubilizes this precious metal. Okay. Now, and the last things I will, this target of today's classes, polymetallic ores. You have sulfide ores in which you have three main metals: copper, lead, and zinc, and you need to obtain three concentrate: copper, lead, zinc. The cortege of copper minerals is presented by sulfide minerals, chalcopyrite, chalcocite, covellite, or there may be bornite or other mineral, but also by some oxidized minerals. Okay, malachite, azurite, cuprite, etc. The ratio between sulfate and oxidized mineral define the processing route. If the oxidized minerals dominate your ore, you cannot use the flotation. Okay, you use the direct leaching procedure in this case. This is oxidized ore. If you have the main part of copper is enclosed in sulfide minerals, in this case you can use flotation. Okay, but at the same time you have the sulfate of coppers, but you have sulfate of leads, sulfate of zinc. How separate and what you need to do? This is a schematic presentation of a step you need to perform to obtain three different concentrates. You start by grinding and classification. Objective and main goal of grinding and classification is obtain the liberation degree. You need ground mineral and obtain in ground mineral you need to obtain the free target mineral particle and free gangue mineral particle. If you have the sulfide ores, this means the ore is composed by 90% from sulfide minerals. You use so-called direct flotation of sulfide. You start, add very small amount of xanthate and frozer, and taking account that in this kind of ore, the chalcopyrite surface is already naturally hydrophobized. Using small amount of collector, you can float the copper minerals, mainly composed by chalcopyrite. You float chalcopyrite in the non-floated product, in the cell product, you have lead, sphalerite, and also pyrite, because pyrite is the unavoidable minerals in the polymetallic ores. All time by the geology, you have this pyrite. Now you need to float the galena. But when you will increase the xanthate consumption, you will float some amount of sphalerite and also pyrite. To avoid the flotation of sphalerite and pyrite, you use depressant. And depressant used is a blend of cyanide and zinc sulfate. These two species form the zinc cyanide in the pulp and selectively adsorb on the sphalerite surface. In this case, the surface of sphalerite is blocked, is covered by the hydrophilic zinc cyanide, and xanthate will not adsorb on the sphalerite surfaces. Adsorption will occur only on the galena surfaces. And this adsorption allows hydrophobization of the galena surface in UV-flowed galena. And in the non-floated product, you obtain the sphalerite and pyrite. And the last step is how separate sphalerite and pyrite. For this, you need activate, because the surface of sphalerite was depressed in this stage, you need activate. And activation occurs when you add copper sulfate in the pulp, and at the same time you increase the pH of solution by using the lime. Okay, and pH is increased up to 10. If you remember table, it's this table here. Where is table? Here, this one. At the alkaline condition, the surface of pyrite is covered by the hydroxide of iron, and this means the surface of pyrite is fully hydrophilic, hydrated, and this allows selectively adsorb the xanthate on the sphalerite surface and float sphalerite, and the cell product you obtain the pyrite. And you can reject this. But to avoid the IMD formation, acid mine drainage formation, modern approach requires to float out the pyrite and separately manage the pyrite, for example, for sulfuric acid production or other, you can make other things. Another way is you can use another flotation approach, which combines the selective flotation with direct flotation, and this means at the first stage you obtain the bulk copper lead concentrate. After using some depressant, you float selectively copper minerals, and the non-floated product you obtain the lead product as galena, or you can use the depressant for copper minerals and float the galena. These two ways, using some kind of depressant, mention it here or here, you can perform the separation. The separation of sphalerite and pyrite is performed as in the previous selective flotation scheme. But the main flotation approach used for polymetallic ore is bulk sulfate flotation. Here, after grinding, with a coarse grinding, you obtain the liberation of sulfide minerals from gangue minerals. You don't need to liberate sulfide between them. You liberate sulfide from gangue minerals. And performing one stage of grinding, and after bulk flotation, you generate not concentrate, but you generate the tailings. The objective is obtain tailings and reject it, and decrease significantly the volume of ore to be processed, okay, for selective flotation. But here, you float using the collector, and main collector used is the xanthate, which adsorbs at pH 8 and 9 on the surface of all sulfate minerals. But after that, you need desorb the collector from mineral surfaces, because to perform the selective separation, you need to renew the collector surface. For this, you need desorb all collector adsorbed on the mineral surfaces. Desorption you perform at high percentage of solid, at high lime consumption. This means that adding 1 kilo per ton of lime, you increase pH up to 11. Okay, and after as a desorption agent, you use the sodium sulfite, and you use very high amount of sodium sulfite because the presence of sulfide ions in the pulp desorbs the xanthate of the mineral from the mineral surfaces. After that, you reground to obtain liberation between sulfate minerals, and you perform selective separation of copper from galena, from lead, and zinc from pyrite. And you obtain 3 or 4 different concentrates. Main difficulty here is to control the desorption process, organize this process. But this process is electrochemically controlled and other controlled by the consumption of the lime and sodium sulfate. You can decrease the sodium sulfate consumption by using some adsorbing agent as active carbon, etc. This is last slide in my presentation. Okay, good. Yeah. If you have some question, we can discuss it.